So the next sample problems we're going to cover as a group. These next 8 problems all have to do with naming compounds, naming ionic compounds, as well as learning to name some simple binary covalent compounds. So in the handout that we had in class, we sort of went through a lot of discussion about all the rules that we have for naming things. So that's what these slides, or these pages really are just some details on how to name these. And so what we're going to do now as we go through and look at these individual questions is we'll put those rules into place. And so again, just plugging and chugging through these, the more of these you do, the easier they're going to become. We talked about it like learning a foreign language, and when you first learn a foreign language, your grammar is probably not perfect. You might think it sounds right, but it's probably not right to someone who speaks the language fluently. And so the more of these problems you do, the more you will recognize things that look right and feel right and sound right, and the more that it will be easy to recognize things that aren't right. So this first sample problem asks us to name the ionic compound that's formed from each of the following pairs of elements. So a few things that we need to think about is when we are naming ionic compounds, we're always going to name the cation first and then the anion. And so the cation is named just as you see it on the periodic table, and then we need to do a little bit of modifying for the anion. So the cation, when we have ionic compounds, is always going to be our metal. And so our first situation here, magnesium is our metal, so that's going to retain its name. And nitrogen becomes our anion. So what we do is we take the prefix, which is NITR, and then we add the suffix IDE. So that's how we would name this ionic compound between magnesium and nitrogen, is we'd name it magnesium nitride. The second one, they've sort of tricked us a little bit here by putting the metal second. But the metal is still going to be our cation, and that's named just as we see it on the periodic table. So this is cadmium. And then iodine, we take the prefix iode, and then we add IDE, so it's iodide. And remember, when you are working through these problems and when you're providing answers on an exam, yes, spelling counts, and you need to make sure that you are writing things neatly enough where I can see what your spelling is. Unfortunately, if I can't read your answer, I cannot give credit when we do these naming problems. Working a little bit more quickly with these last two, strontium is our metal, and fluorine becomes fluoride. Last one, again, cesium is our metal, and sulfur becomes sulfide. This next problem, actually I'm going to leave this here like this, is actually related to the previous sample problem. Is now we're asked to actually provide the empirical formula. What is the ratio of the cation to the anion in the compounds that we have above? So that requires us to think about the charges that we're going to have on these. So magnesium, being found in the alkaline earths, is going to have a 2+ charge. Nitrogen, found in group 5, means it's going to gain 3 electrons to be 3-. And one of the skills that we learned about was sort of this crossover method, that we can initially take what was the superscript, the charge on each of these atoms, and allow it to become the subscript on the adjacent or the complementary atom. And so in this case, we're going to have Mg3N2. One of the things that I really like about a lot of the sample problems that they have is each problem is a new way to think about something that allows us to apply something new and different. So we'll see that as we go along here. So cadmium, again being in the same group as magnesium, is going to be cadmium 2+. Iodide is I-. Again, if we do that switch, we can see that we're going to have Cd I2 for cadmium iodide. With strontium and fluorine, strontium is another what we call divalent 2-charged ion. Fluorine becomes fluoride as -1. So that becomes SrF2. And then cesium here is now going to be monovalent, where our anion is going to be divalent. And so we get CS2S. Okay? Moving forward and thinking about some other examples, now we are given the name and we have to provide the formula. And what's unique about these are these represent metals that have the potential to have different charges. So with this one, when we see tin with a Roman numeral 2 in parentheses, that actually tells us that it's the tin that could have a 2+ charge. Fluoride is F-, and so putting these together and applying the skill from above, this means that this is going to be SnF2. So this is chromium Cr, and then iodine, which becomes iodide. So we're going to have Cr3+, and then we're going to have I-. So this is again providing a name rather than the formula. So when we break this apart, we're going to have a chromium with a 3+ and then iodide. So this tells us that we are going to have chromium 3 and then iodide. So one of the things that we have here with some of these compounds that can form more than one charge is we have the us and the ick that we could have. So chromium is something that could either exist as chromium 2+ or chromium 3+. In this case, we have the higher number, and remember that we want to say if we are larger because we've eaten too much, we feel icky. So this could also be chromic iodide. So if you are asked to provide the name, either one of these names would be correct, but you want to know how to name these both ways, because if you were given chromic iodide and needed to provide the formula, you'd need to know that that was chromium in the 3+ state. We see that here, that example here with ferric iodide. So again, iron is something, I'm going to write this down here, iron is something that could come as 2+ or iron 3+. Again, if we are in the icky state, as we see here, that tells us that it's the larger charge, so we're going to have iron 3+. Oxide is always O2-. So in this case, by doing our crossover that we learned in our last sample problem, that's Fe2O3. Now again, with this cobalt example, they give us the formula, so we know that it's cobalt 2+. Sulfide is going to be S2-. And so in this case, we know that for that cobalt, and again, cobalt is something that could exist as cobalt 2+ or cobalt 3+. This is going to be cobalt 2 sulfide. And because cobalt again could be cobalt 2+ or cobalt 3+, this cobalt is the lower of these. Now for this one, we don't tend to have the ick and the us that we see here. So for this one, this really is the only way to name it, is cobalt 2 sulfide. Moving to our next problem here, again, give the name, systematic name for each formula, or the formula for each name for the following compounds. So what we've moved on to with sample problem 2.10 is thinking about polyatomic ions. So the previous problem really just dealt with what we call monoatomic ions, ions that are just a single atom. In this problem, we have polyatomic ions. And so these are ions, negatively or positively charged groups of atoms that we're going to see in compounds. So for our first one here, we've got iron that's going to be 2+, and then ClO4 is going to be minus. So some of these we're just going to have to know that some of them are 2+ or 3+ or -1 and so forth. And so all of these halogen oxygen ones that we're going to see are going to be -1 charged, so monovalent anions. In this case, we can name this one as iron 2. Now this guy is tough. When we have these guys that have the oxygens and the halogens, we have to think about these rules. There's going to be a hypo, which means the lowest, and then we're going to have ites, eights, and then per eights. So the first ones are going to be these hypo ites, and then the ites, then the eights, then the per eights. So this is kind of the order that we have of these. Now, this has to do with the fewest number to the most number of oxygens. And so in this case, we have the most number of oxygens. So this is going to be per. Chlor is the prefix, 8. So those are kind of complicated. Again, you can just make flashcards and memorize, or if it's easy to kind of think about the hierarchy that we have for these, you can apply that to any of the halogen oxygen systems, because this also comes in a bromine flavor and an iodine flavor as well. So there's actually 12 of them that we need to be able to think about. All right, sodium sulfite. So sodium is pretty easy. That's always Na+. But the sulfite, we have to remember that that is not the SO4, that's the SO3. The ites are going to be the lower number versus the eights. And these are -2 charge. So again, these are ones that not only do we have to remember the ites versus the eights, but we have to remember their charges as well. So this guy ends up being Na2SO3. This last little one introduces us to the concept of thinking about water that we can have associated with an ionic compound. And in that case, we need to indicate the number of waters that are present. And so this water is called a hydrate. And so we first have to name the salt, and then we have to put the word hydrate at the end with a prefix that tells us how many waters. So this guy is going to be barium hydroxide, and then octa for the 8 waters, hydrate. So lots of complicated stuff with naming in this last sample problem. So practice lots of problems with polyatomic ions. Table 2.5 in your book has the common polyatomic ions. So again, making flashcards of those is going to be really helpful. Remembering that this halogen oxygen series comes as a whole bunch of different flavors. As we move through our naming here, there's going to be several of these problems where it asks us to think about an error in what we see. So in this case, it tells us that there's an error in the second part of each statement. So we want to assume that the first thing is what is correct, and we have to fix the second thing. So for the first problem here, we can see that it's barium, and then this C2H3O2 is called acetate. So even though it looks like there's nothing wrong with saying barium diacetate, we don't use these Greek prefixes with ionic compounds. So not with ionic compounds. We're only going to use those prefixes to indicate number when we're talking about the number of waters that we might have here, or in a problem that we'll get to in a little bit, we're going to talk about non-covalent compounds, and we're going to have to use those prefixes there. Sodium sulfide has the formula Na2SO3. Well, this is not sulfide, this is actually sulfite. So if we wanted to have sodium sulfide, that would be Na plus and then S2 minus, so that would be Na2S. Iron sulfate has the formula Fe2SO43. Well, if we saw this guy, that would actually be telling us that we would have iron in the 3+ state. This tells us we have iron in the 2+ state. So iron in the 2+ state, sulfate is -2, and even though we might want to write Fe2SO42, we always want to have things in the simplest whole number ratio. So that's going to be 1 iron for every 1 sulfate, and that's FeSO4. We don't have the 2's in there. The last problem here sort of reminds us that the only time we want to use parentheses is if we do have more than one of something. So cesium carbonate, this is the correct formula in that we're going to have 2 cesiums, but there's only 1 carbonate, and so we don't need to have that parentheses. So to correct this, it would just be CS2CO3. Moving on to the second page here of problems that we have here. Name the following anions, which seems pretty straightforward, but part of this problem is getting us to think about how we would have the acid that's derived from that anion be named. So in this case, this Br- is called bromide. When we're naming acids, especially when we're naming the halogen series of acids, we need to add the prefix hydro in front. So this is hydro. We take the prefix from the anion, which would be brome. We add the suffix ic, and then we add the word acid at the end. And the acid that's made there is HBr. This next one, if we were to name this anion, it would be iodate. Now we only use that prefix hydro when we have these halogen acids, or we'll see we actually are going to use it again in part C here. But we don't put the hydro in front of every single acid. And in this case, we're going to take the prefix, which is iode. We're going to add the new suffix ic, and then we're going to add the word acid at the end. So this is iodic acid. This is cyanate. That's what we have as cyanide. For our next example, this anion, it's a polyatomic anion, is called cyanide. And so we take the prefix, cyan, we add ic, add acid to the end, and this is another one of those weird ones where we do have hydro in front of it, and so that's HCN. Again, if you didn't have hydro in front of that one, I wouldn't be too persnickety about that, but this one technically is called hydrocyanic acid. Fourth one here, anion, is called sulfate. This one's a little bit weird. We actually need to use more than just the root here, more than just the SULF. We actually are going to use the full name, sulfur. We're going to add ic at the end, sulfuric acid. And again, providing the formula for this one's a little bit different from the other ones, in that having this -2 charge on our polyatomic anion means we need to have 2 hydrogens in order to fully balance the charge. Last one here, we've got nitrite. So in this case, the ITE is going to become OUS, so nitrous acid, HNO2. Again, the rules for acids are kind of complex compared to other things. There's only going to be 1, maybe 2 acid questions for nomenclature on the test, so don't stress too much if that's a challenge for you. Focus on more of the other naming. So the next problem, again, provide the name or formula as appropriate. We're moving on to now talking about binary covalent compounds. So binary meaning 2 atoms, covalent meaning we're grabbing 2 things from the right side of the periodic table, 2 nonmetals. And what we do when we have 2 nonmetals is we have to consider who is most metal-like. So who is the furthest to the left? So we have to sort of name this as though one was more metal-like. So ask yourself the question, is who is closest to the metals, that is going to be named first, and it's also going to be treated as such, and so it's going to retain its name. So when we say carbon disulfide here, well, carbon is going to be more to the left, more metal-like than the sulfur. But even with this guy, because we have the name already provided for us, it tells us who's more cation-like, who's going to be written first, the carbon. And then sulfide is S2-, and we need to have this 2 here because that 2 is what tells us that 2. Next problem here, the name of PCl5. Well, P is written first, so we're saying that that is more metal-like, so that's going to be phosphorus. And then we're going to have 5 chlorines that are anion-like, so we're going to call them chlorides. So this is pentachloride. Now this last problem asks us to think just a little bit further because they're just telling us that we're having nitrogen and oxygen together. We've got 2 nitrogens and 4 oxygens, but we have to have this thinking about who is closest to the metals so we know who is written first. Well, nitrogen is in group 5, oxygen is in group 6, so nitrogen is more on the left, so that's written first. They tell us that we have 2 of those oxygen atoms and then 2 of the nitrogen atoms and 4 of the oxygen atoms. Now going ahead and naming this, knowing that nitrogen is more metal-like, it retains its name. So this is dinitrogen tetraoxide. So the next problem looks at another one of these examples of, okay, here's one part and then a second part that's incorrect. So help us correct the second part. So this problem, first one looks at SF4, saying that we want to call it monosulfur pentafluoride. Well, there's actually 2 things that are wrong with this. We don't need to use the prefix mono here. So that's the first part. And then the penta is incorrect because it should be tetra. So this is sulfur tetrafluoride. The next one, dichlorine heptaoxide. Well, hepta would mean 7. So this is going to be Cl2O7. And then N2O3 is dinitro trioxide. Now the problem is that when we're naming our binary covalent compounds, the first one, which we're saying that behaves like a metal, is given its full correct name as you see it on the periodic table, if you will. So this is dinitrogen trioxide. So the last 2 problems here incorporate the next skill that we're learning, which is thinking about molecular or formula mass. So again, molecular or formula mass really means adding up the weights, if you will, of each atom that is part of either a covalently bonded molecule or the unit of an ionic compound, which we call a formula unit. So this first problem, tetraphosphorus trisulfide, and I have a mistake there, that shouldn't be an extra S that's in there. So trisulfide, that S is not there. With this first one, again, it kind of combines a couple of skills here in that we need to think about how to take this name and actually make it into a correct formula, and then we need to use that formula to get the mass. So tetraphosphorus is going to be 4 phosphorus atoms, and then trisulfide, 3 sulfurs. So one of the things we should realize, again, another thing that I could ask with this question is this an ionic or covalent compound? And this is a covalent compound, because we have two nonmetals that we've bonded together. And that's also why we need to have these prefixes to indicate the quantities of each atom that we have. So if we're figuring out, in this case, it's going to be the molecular mass, because we have a covalently bonded molecule, we're going to take 4 times the atomic mass of each phosphorus atom, which is 30.97 atomic mass units. And we're going to add that to 3 times the atomic mass of sulfur atoms, which is 32.07 atomic mass units. Add those together, and we're going to get 220.09 atomic mass units. Now, even though it looks like maybe we should be rounding this to 4 significant figures, we probably have that in our head because we've been doing so much multiplication. Remember, when we are adding or subtracting things together, we need to look at the number of significant figures to the right of the decimal. And almost all of the atoms on the periodic table are listed to atomic masses of 4 significant digits, which for many of them mean that they're going to have 2 decimal places to the right of the decimal point, which means we want to maintain that in terms of the significance in our final answer. So our final molecular mass will actually gain a significant figure because of how the math is performed there. So ammonium nitrate, again, we need to remember that ammonium is NH4+, nitrate is NO3-. With these, we know that it's a 1-to-1 ratio, so it's NH4 NO3. This problem could be made a little bit more complicated if one of these polyatomic ions was more than monovalent, having a charge more than plus or minus 1, because that would scale up one or the other of the polyatomic ions to be able to balance the charge. In this case, this is an ionic compound. So this is an ionic compound, and being an ionic compound, we have a formula mass. So in this case, we've got nitrogen in both of our polyatomic ions, so there's 2 of them, each coming at 14.01 atomic mass units. We've got 3 oxygens at 16.00 atomic mass units, and then 4 hydrogens at 1.008 atomic mass units. Add those all up, and we're going to get 80.05 atomic mass units. Our last problem here kind of pulls everything together and asks us to think about molecular scenes. It asks us to think about different kinds of compounds, whether they're ionic or covalent, and then lastly determine a formula or molecular mass is relevant. So let's take the compound on the left. I'm just going to kind of highlight some other types of questions you might see or be able to think about with this. When we have sodium and fluorine that are together in a compound, we know we're going to have one of them as a cation and one of them as an anion because we're grabbing from 2 sides of the periodic table. We have a metal and we have a nonmetal. So a question that I could ask is this an ionic or a covalent compound? Well, this is going to be an ionic compound, and the formula is going to be NaF. In doing so, and having an ionic compound that has a formula unit, we're going to have a formula mass that we calculate. So that formula mass is the mass of 1 sodium cation, 1 sodium atom, which is 22.99 atomic mass units, plus 1 fluoride atom, which is 19.00 atomic mass units. Add them together and you get the formula mass for sodium fluoride as 41.99 atomic mass units. The last thing that we needed to answer for this question is we needed to actually name this compound. So naming an ionic compound, we name the metal first, and just as we see it on the periodic table, the fluorine becoming fluoride for our anion. Let's take the substance that's on the right. Our molecular scene shows individually, discretely bonded atoms. And we can see also that these atoms are nitrogen and fluorine. So in grabbing 2 nonmetals, we also know that we have a covalent compound. We can see from counting the atoms that we have in our molecular scene that the molecular formula is going to be NF3. naming this compound, and I sort of gave it away here, the N has to go first because N is furthest to the left on the periodic table. Nitrogen is in column 5 in the periodic table, where fluorine is in column 7, so that's the halogens. So nitrogen is more towards the metals, and so it's written first. And so when we name our compound, it's going to be called nitrogen. And then we have to use a prefix to indicate the number of anion-like species, which is the fluorine. So we have to say tri. And then fluorine becomes named like it was an anion, and we say fluoride. If we figure out the molecular mass for this, because this is a covalent compound, we're going to have molecules. We can take that there is 1 nitrogen at 14.01 atomic mass units plus 3 fluorines at 19.00 atomic mass units. Add those together and you get 71.01 atomic mass units for each nitrogen trifluoride molecule.